Morning, everyone. Questions about the homework that was due last night or tonight? Oh, did you? Okay.
The one that was due last night, yes.
Which was the central tendency and the variability stuff, right? I think the question you'd ask me, the data it was given you isn't something you would put in your calculator. You'd basically just plug it into that shortcut formula because it was already giving you the sum of x and the sum of x squared and the n value. It didn't actually tell you what the actual observations were. Does that make sense?
Yes.
Okay. Which if we have that data, we don't really care if we're just finding the range and standard deviation. Any others? What? Or from tonight? Morgan, did you have a question?
I wasn't here yesterday, so
You're kind of behind on it? Okay.
yeah, I have questions on the work that was due last night.
Okay. Did you watch the videos?
I
Maybe
started it. I haven't watched the
Okay.
anything.
Okay. So what I'm going to do today, I'll pull up the book and we'll kind of talk about what we did yesterday. And then I'll go in and do the two sections for today. 2.8 will take a little while. 2.9 is really short, so it won't take that much time. And then at the end of class, I'll give everybody a study guide for the test on Thursday. Does that sound good?
No.
No? All right. So yesterday we talked about this section, which is interpreting the standard deviation, which basically is a combination of putting together the mean and the standard deviation, right? It's the combination of those two things. The two rules that we covered are, the first one is called Chebyshev's rule. Chebyshev's rule applies to any distribution regardless of the shape of the frequency distribution. So whether it's, it could be skewed to the right, it could be skewed to the left, as both this graph's skewed to the right, this graph's skewed to the left. Right? Remember, when we're talking about skewness, your mode is always where the peak is, and then it will go your median, and then your mean is pulled farthest to the right, because these outliers out here have an influence on the mean. So that's skewed to the right? That's the distribution of how the mode, median, and mean are. Same with skewed to the left. The mode is still right here where the peak is. The median is in the middle. Remember, the median is always at the 50th percentile. Right? It means half of all the data lies below the median, half of all the data lies above the median, right? And then finally the mean. So you notice the mean is always pulled towards the tail, right, or the outliers. Today we're going to talk a lot about outliers, all right? Techniques for identifying outliers. So these two distributions, this one's skewed right? Skewed right. This one's skewed left. And then we have our normal distribution, where the mound's right in the center. And the mean, median, and mode all lie directly in the middle. All right? That's our normal. So regardless of the shape of the distribution, Chebyshev's rule applies. All right? So remember, within one standard deviation, we really don't have any information when we're dealing with Chebyshev's rule. We don't know how many of the observations will fall within one standard deviation below and one standard deviation above the mean. With Part B, notice we do have an idea. Part B and Part C. Part B, within two standard deviations, at least 3/4 of the observations, or 75%. And for Part C, at least 8/9, or what was it, 88.9% of the observations lie within 3 standard deviations. This is for any data set, regardless of the shape. And what I want you to notice here is the words "at least." So what this means is, we know that there is 75%. There could be more than 75% of the observations within 2 standard deviations, but there can't be less. That's what this "at least" means, all right? And when it says at least 75%, that's a hard floor, all right? There can be more than 75%, but there can't be less than 75% of the observations or measurements that fall within 2 standard deviations. Same with 3, we have the words "at least." Within 3 standard deviations, there's at least 8/9, which is 88.9%. And then we have a general form given any k. So you tell me how far from the mean you want to go, and I'll tell you what percentage of observations will lie within that interval. All right? The other one is the empirical rule. The empirical rule only deals with normal distributions. Right? The empirical rule only deals with normal. Notice the start words here. It does not say at least 68%. It says approximately. So that means there could be a little bit less than 68% or a little bit more than 68%. Does everybody see the difference between at least and approximately? All right? Now, they kind of just seem like arbitrary words that are thrown in there, but they have a very essential meaning. So the empirical rule, what I want you to remember, is 68, 95, 99.7. 68% of all measurements will fall within 1 standard deviation. So if this is my mean of my normal, right, and I'll write that over here since it's getting kind of small. So my mean, in a normal distribution, the mean, median, and mode are all right in the middle, right? Mean, median, mode. They're all the same value, or approximately the same value. So I can call this X bar if it's a sample, or mu if it's a population. Then if I go 1 standard deviation below, I'm going to call that X bar minus, I can't go sigma, I can't mix mine. X bar minus S and X bar plus S. What that's saying is, in this entire interval is 68%. So on either side of the mean, there's exactly 34%. Right? That's within 1 standard deviation. I'll go ahead and show the graph that's a little bit easier to read. There it is. So within 1 standard deviation is 68% of the data. Within 2 standard deviations is 95% of the data. So if I take 68 plus 27, you come up with 95, right? 13.5 plus 13.5 is 27. 27 plus 68 is 95. And then out here, 3 standard deviations away from the mean, which will be about right here and right here, we showed we're, about 2.35, wasn't it? And then the outliers outside of 3 standard deviations was only 0.3% of all the data, or 0.003 as a decimal. Right? So the stuff we discussed yesterday is very important in moving forward in this class. All right? Understanding what's going on in here. This percentage, another way to think about it, is this is the percentage of the total area under the curve. Right? If I was going to call all the area under the curve 1, right here in this little trapezoid-looking thing, it's not quite a trapezoid, that's 34% of the data. Or 34% of the area under the curve is another way to think about it. Okay? And this dealt with battery life, right? And we saw that the battery had a warranty at 36 months, which is way down here, right? The reason they put their warranty at 36 months is because almost all of the batteries will last longer than that. So basically all the warranty is a lemon guarantee, right? If you get a really bad battery that doesn't make it into any part of the curve, right? If you happen to get one of these batteries that live way down here, then they'll replace it for you for free. That's what that's saying. Now we had another interpretation for these values. Rather than call this mu, we gave it a value that was a z-score. Then this value right here, which is 1 standard deviation above the mean, we gave it a very specific value, which is a z-score as well. We have a formula for calculating the z-score. Z-scores are nice because it tells us the distance from the mean, and the unit is the number of standard deviations. All right? That's in the next section. All right, and then we talked about percentiles. I really want to hit this again because we use these percentiles in today's discussion. All right? This percentile deals with, how you score on your ACT or SAT. They say you score in the 75th percentile. That means 75% of all the people that took the test scored less than you, 25% scored more than you. What was 75% called? Do you guys remember from yesterday? What did we call it? Upper quartile. The upper quartile. Today we're going to deal with the quartiles when we create what's called a box plot. All right? So we messed with that, talked about percentiles. The median is always the 50th percentile because the median is defined as half the data lying below it and half the data lying above it. So here's our definition of quartiles. The lower quartile is the 25th percentile of a data set. The middle quartile is the median, or 50th percentile. And the upper quartile is the 75th percentile. Now, these are not quite broken down into quartiles, all right? Because below 1 standard deviation was only, 17%, right? It was 2.5 plus 13.5. Not 16%. Right? So you'll notice if we go back and look at that curve, which I think we have it on the next page. Yeah, I'll mention that once we talk about z-scores. So, then we come up with a standard way of talking about mean and standard deviation. We give it what's called a z-score. You weren't here yesterday, write those formulas down, all right? Z is equal to x minus x bar over s. What that means is whatever the measurement is minus the mean divided by the standard deviation. That's a way to generalize what the value is in relation to how far it is from the mean in terms of standard deviations. Is the observation 1.5 standard deviations from the mean? Is it 2 standard deviations from the mean? Right, so the unit of the z-score is standard deviations. And the standard deviation changes depending on the experiment. That's why we have to use the standard deviation in the formula for calculating z-score. All right? Okay. Then we did Joe Smith's score. Here's an interpretation of z-scores using our empirical rule. Approximately 68% of the measurements will have a z-score between -1 and 1. That's exactly what's going on here. Notice the coefficient on S is basically the z-score. Right? The coefficient right here, there's a 1, even though we don't explicitly write it. There's a -1s and a +1s. And then we get out here and have a x bar minus 2s. Notice that's basically just a -2, right? It's the coefficient on S. And here's x bar plus 2s. And in here was 13.5%. 13.5%. Then out here we have x bar minus 3s. And finally, x bar plus 3s. Was it 2.35 right here? Remember that correctly from yesterday?
Yeah.
2.35%, 2.35%, and then out here was 0.15% and 0.15%. So you'll notice the 25th percentile, where 25% of the data lies below it, is actually this piece plus this piece plus this piece, which is 16%. Plus we need another 9%. So actually the 25th percentile is going to lie right about here. Right? And let's just put a dashed line. So that's going to be the 25th. I'll put TH. Which is also known as our QL, right? And approximately right here is going to be our 75th, which is going to be QU. So the z-score for the 25th percentile isn't going to be exactly -1. It's going to be a decimal value. The 25th percentile is about 0.8 standard deviations below the mean, give or take. Because it's less, because 1 standard deviation below the mean, right, there's not 25% of the data here. We need to steal another 9% of the data from that piece right there, right? And we'll systematically find that number in the future. And then if I flip to the next slide, here's basically the same shape. It's just I've filled in the area portions, right? So this is z is 0 at mu. Mu plus sigma is 1, right? Because that's 1 standard deviation above the mean. When it's negative, that means it's 1 standard deviation below the mean, right? So 99.7% of my observations lie between -3 and +3. Almost, essentially all of the data, right? Anything that lies outside of 3 standard deviations, we're going to call outliers, all right? Anything that lies outside of 2 standard deviations are what are called potential outliers, right? This is what we have to do for your homework that's due tonight, right? So that was a very quick synopsis of what we talked about yesterday, okay? Which went very quick. So this type of z-score stuff does not work with these 2 types of distributions. It only works when it's normal and symmetric, okay? These 2 are not normal and symmetric. The reason I know they're not is because the median and the mean are not equal. The mean has to be the 50th percentile. Does that make sense? That's what's happening in a normal distribution. Here, the mean is not the 50th percentile. Okay? And once again, this is an approximately 68%. Whereas Chebyshev's rule gives us the at least, which means it can't be less than, but it can be more than. Right? But Chebyshev's rule says in 2 standard deviations it was 75%. Right? In our empirical rule, remember, within 2 standard deviations, it was 95%. So a lot more data lives within. We can guarantee there's a lot more data within 2 standard deviations if it's normal. Okay. So now for the new stuff. All right. Methods for detecting outliers. And we'll actually come up with a nice systematic definition of what constitutes an outlier. Right? And basically where they come from. Right. Sometimes it is important to identify inconsistent or unusual measurements in a data set. Right? If we're pulling temperatures from March and they're all right around 70 and all of a sudden, at noon, and we go out every day at March at noon and we take the temperature. They're always got to be, right around 70, 68, 74. And one day it happens to be 38 degrees outside. That's an outlier, right? Is that because of a natural phenomenon? Is that because our data reading our instrument reading the temperatures messed up? Or is it human error, right? What contributes to that outlier? An observation that is unusually large or small, so it can be really, really big or really, really small, right? Relative to the data values, of course, everything's relative, right? We want to describe is called an outlier. So something that's really big or really small relative to all the other data values. Okay, and we go over an example with our gas mileage problem. Outliers are often attributable to one of several causes, right? And here they are. Rather than read through that paragraph, let's just read this blue box right here, this Reader's Digest version. Let me zoom in one more time. An observation or measurement, look, notice I've been using those two words interchangeably, and there it is again, right? I like to use the word observation rather than measurement, because observation includes qualitative data. Measurement pretty much just points towards quantitative data, right? And I know we're not talking about qualitative data right now with this stuff, but that's a good habit to get into calling it an observation rather than a measurement. An observation that is unusually large or small relative to the other values is called an outlier. Outliers are typically attributed to one of these three causes. First, we've done something wrong. The measurement is observed, recorded, or entered into the computer incorrectly. I went out and took the temperature and my thermometer was broken. So it registered 38 degrees. That's what I could contribute or attribute that outlier to. The second is the measurement comes from a different population. Maybe I went out and took the temperature at 9 in the morning when I was taking the temperatures at noon, right? That's a different population. Everything has to be the same when you're taking that temperature. You can't take it at a different time of day. So that's what it could have been from. And finally, number three, it could have just been by chance. It could have been a rare event, right? R-A-R-E, rare, which means it doesn't happen very often, but it did happen. And those things do happen sometimes. That's why we want to pinpoint, we want to get rid of, if our outlier came from one of these first two causes, we just want to throw it away, right? It doesn't really do anything for us. But if it came from the third cause, we want to do a little more investigation into why. How come that outlier was there? What happened? Maybe if we're measuring fish in Oasis State Park, right? And they're all about 2.5 feet, some are 1, and then we get one fish that's 8 feet long. Where does that come from? Maybe that fish was hiding out somewhere, found a certain spot, or found a food source, or maybe it's a different type of fish than is in the pond. All right? Which happens sometimes. And those rare events, those change the idea. Because it happens sometimes. It changes the idea of the scientists with whatever experiment they're conducting. Okay, there's two useful methods that we're going to talk about for detecting outliers. One graphical and one numerical. All right, so one by looking at a graph and one by actually looking at the values in their numbered form. Okay? Of course, the graph, it's easier to identify because you just look at it, right? Our box plots and z-scores. So z-scores we've already talked about. A box plot is what we're going to start to build today, okay? The box plot is based on the quartiles. Remember, the quartiles are 4 quarters, right? 0 to 25, 25 to 50, 50 to 75, and 75 to 100. That's our 4 quartiles. Quart means 4. Defined in section 2.7 that I just talked about. of a data set. Specifically, a box plot is based on the interquartile range. So write that down, IQR. And notice how it's called a range, because it's basically the high value minus the low value. But it's not the highest value in the entire data set. It's just the upper quartile value minus the lower quartile value. So it's a range, it's a form of a range, because we're taking a difference of two measurements, but it's not the range that was defined in section 2.5 that was the maximum minus the minimum. It was just the upper quartile minus the lower quartile. All right, so the IQR, which is known as the interquartile range, is QU minus QL. What percentage of the data should be in there? What is QU? What percentile? 75 is QU, the upper. Right. So 75, another way to think about the IQR, is equal to the 75th percentile minus the 25th percentile. So what is that? 50. Basically, 50% of the data will be within the interquartile range, or exactly 50% of the data, because that's how we define QU and QL. Let's read this box. It'll basically talk about what I was saying. An annotated Minitab box plot for the gas mileage data. Remember the gas mileage data we talked about all semester last week? Right, there was, what, 40 measurements, or was it 50? They were all right between 30 and 44.9, right, was our data. It's shown in figure 231. Note that a rectangle, the box in the box plot, is drawn with the bottom and top of the rectangle, the hinges drawn at the quartiles QL and QU. So we put a hinge on the 25th percentile and the 75th percentile. We call those hinges, just like on a door, right? Respectively. Recall that QL represents the 25th percentile, and that should be a lowercase l, that's a typo right there. See how it's not a little l? They write it with a little l right here and right here, but then they put it as a big L right here. But that should be a little l. QL, which means lower quartile, represents the 25th percentile, and QU, which is the upper quartile, represents the 75th percentile, which means 75% of all the data lies below it. Okay? Recall that QL, okay, by definition, then the middle 50% of the observations, which is exactly what I've come up with here, this is the 50% of observations that are right in the center. We've kicked off the bottom 25% and we've kicked off the top 25%. Okay? Those between QL and QU fall inside the box. For the gas mileage data, these quartiles are set at, so they've came up with these numbers. All right? Basically, they picked this 35.625 number so that 25% of all the observations lie below it. This is not a data value that was in the data set. This number was not in the data set, right? This is a number that we basically draw a line to create a hinge. Okay? So we'll look at a graph of that gas mileage data again so that we can get an idea of what it looks like. So remember those numbers, 35.625 and 38.375. You notice they're pretty close together. So most of our data lies right in the middle, right? Do you remember that from our gas mileage data? Let me go look at it. Page 40. So here was a histogram of our gas mileage data. So there was 100 observations, that's right. So exactly 25 of our observations lie below 36.625. and exactly 25 lie above 38.375. So most of our data, notice, lives right here. That's the middle 50%. That's the outside 50%. Or, yeah, 25 below and 25 above, which is another 50%. So we see kind of what's going on here with the quartiles, what they kind of represent. There's a dot plot here, which is another way to look at it. Looking at this dot plot, you can kind of guess what are going to be outliers. Kind of looks like there's data that's far away, right? Way below or way above the rest of the data. So let's count these dots. And I'm going to stop when I get to 25. And hopefully where I stop is going to be 36.625, right? So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So it's going to be right in here. Right? These dots are kind of estimates. That's why they're put where they're at. But it looks like right about here is where our QL is, right? Our lower quartile. And our upper quartile is going to be about 38, which is about right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Right? So basically if I drew a line right here and right here, this is my middle, my inner quartile range. Notice half of the observations lie within that, right? So this is the data we're talking about here in the book. So let's flip back to page 78. And it's nice doing this gas mileage one because there's exactly 100 observations. So 25% is 25 observations, right? Which doesn't happen all the time. That only happens when you have exactly 100. So IQR is QL minus QU. And these numbers were basically, see how they have a 5? There must have been like a 3.6, a 38.36, and then a 38.38, and then they just pick the value in the middle. They basically take those two numbers and find their median. That's why there's 3 digits in these QL and QU, because it basically splits it in half. That's why it's a 5 as well. Because all of our data only had 2 decimal places, right? Our gas mileage data. Okay. The median is shown at 37 by a horizontal line within the box. We've already found that out. The median was 37, which means exactly half lie below 37 and exactly half lie above 37. So that's how we create the box, all right, to the box and whisker. To guide the construction of the tails of the box, 2 sets of limits called the inner and outer fences. So the fences are outside of the hinges, all right, are used. Neither set of fences actually appears on the plot. Inner fences are located at a distance of 1.5 times the IQR, times the inner quartile range. Which basically, a way to think about it is that's 1.5 standard deviations. That's kind of a way to think about it, right? It's not exactly that, but that's a good way to kind of wrap your mind around it, okay? Emanating from the hinges of the box are vertical lines called the whiskers. The 2 whiskers extend to the most extreme observations inside the inner fences. For example, the inner fence on the lower side of the gas mileage box plot is. So that is our formula for the lower inner fence, and then I'll write a formula for the upper inner fence. So this IQR that appears in here is this same value, right? It's QU minus QL. The lower hinge occurs at QL. So I could write that as QL minus 1.5 times the IQR, right? And all these formulas will be given to you on your test. So let's rewrite both of those. So the lower inner fence is equal to, and I'm writing that a little too big, let me write it a little smaller. So the lower inner fence is the lower hinge, which of course the lower hinge was defined as QL. So the lower hinge is wherever the 25th percentile is. Notice how lower hinge, they write the number 35.625, which was defined as the lower quartile. So I'm going to go ahead and just call it QL. So the lower inner fence is QL minus 1.5 times IQR. Where that number 1.5 comes from is beyond the scope of what we're going to talk about. All right, that's basically just the way the formula is. So you just have to trust me. All right, take it with a grain of salt. So there's a lower inner fence and then there's an upper inner fence. Which is equal to QU minus 1.5 times IQR. Oh, I think that's plus, actually. Let me go look at it. Yep. Which makes sense. Yeah, you're going to find where the upper hinge is and then add something to it, right? You're not going to take something away from it. So to find the lower fence, we find the lower quartile, we find our 25th percentile, and then we're going to move a little bit left of it. So we're going to find our 25th percentile, but then move down a little bit. And then we're going to find our upper inner fence, we're going to find our 75th percentile, and then move up a little bit. So we're going to get more than 50% of the data inside these fences. Not a lot more, but a little more. Although box plots can be generated by hand, the amount of detail required makes them particularly well suited for computer generation, as most of the graphs in this course. The histograms are pretty easy to do by hand. The stuff where we draw nice straight lines. But box plots, we use computer software to generate the box plots in this section. So let's look at the next page. So here it is. The way that they came up with this value right here is QL minus 1.5 times IQR, times the inner quartile range. And let me jump back to the next page, the previous page, to look at what that number was. So the lower inner fence should happen at 31.5. The way they come up with that is 1.5 times the IQR. The IQR was QU minus QL. So notice, once you have QL and QU, you can come up with all this stuff, right? All this stuff derives from the upper quartile and the lower quartile. So 31.5 is where our lower inner fence is going to be. And our upper inner fence is defined right here, should be 42.5. It's our upper hinge, or our QU, plus 1.5 times our IQR. So 42.5. So it should happen at 31.5 and 42.5. And as we look at this graph, 31 is going to be about right here, right? So 31.5 is about right here. If you draw a line straight across, pretty close, right? Was it 31 or 32? 31.5. So that's why it's better for computer generation. So that we get this line, we draw it exactly to 31.5. So if I was going to draw a straight edge right across right there, right, it would basically hit about 31.5. Same up there, it would hit about 42.5. So 43 is right here, 42.5 is right here. If I drew a line straight across, boom, it hits our upper inner fence. So these stars are something pretty important. There's another name for the star, starts with an A, what do we call them? An asterisk, right? Those asterisks denote outliers. You'll notice that it's at 30.0, and it looks like 45 almost, right? Or 44.9. 45 would be about right here. Boom, that's where the asterisk is. So anything that lies outside of these fences, we're going to call an outlier. So how do they construct this? Well, the median is 37. That's the number that's in the middle. That means half the data lies below 37, half the data lies above 37. Basically, in this region right here is 25% of the data, because this number is QL. That is the lower quartile. So you'll notice most of this data lives right in the middle. That's why those boxes aren't really big, especially in relation to the whiskers. See how the whiskers look a lot longer? That's because our data is a lot more compact. Right? Our IQR, our inner quartile range for this was pretty small. It was 2.5. Right? 2.75, which isn't a very big number in relation to the values in the data set. Okay? So the smallest measurement inside the fence, or the whisker, the smallest measurement inside this whisker is the second smallest measurement, 31.8. 31.8 does lie within that fence, right? Because that fence extends out to 31.5. Thus, the lower whisker extends to 31.8, so it stops at 31.8. Similarly, the upper whisker extends to 42.1, the largest measurement inside the upper inner fence. So see how our whiskers actually stop before our fences? It actually stops at the last observation within the fence. So that's why it's not exactly 42.5, it's 42.1. Because that's the last observation within the fence. So right at the end of that whisker is our very last observation that occurs within the fence. Right here is our very last observation that occurs within the fence. All right? Values that are beyond the inner fences are deemed potential outliers because they are extreme values that represent relatively rare occurrences. In fact, for mound-shaped, right, we saw that 0.3% lies outside, or 0.15% lies below one standard deviation, and 0.15% lies above one standard deviation. It says for mound-shaped distributions less than 1%, it's actually less than 0.5% lies outside of that. Two of the 100 gas mileage measurements, the smallest one and the biggest one, fall beyond the inner fences, one on each end of the distribution. Each of these potential outliers is represented by a common symbol, an asterisk in MyMathLab. You'll notice in sports records, right, whenever somebody sets a record and maybe it's a sprint record and they're running downwind, so it's wind aided, they put an asterisk by that record, right? Because that means that it's a potential outlier. It's something that's not, it's a rare occurrence. It's something that's not going to happen all the time. There's basically some other influence, some other factor that's influencing that score. Just like with the home run records and steroids, right? They want to put an asterisk on it because it's an outlier. Especially if you look at the last 4 or 5 years in baseball, right? The home run totals have really dropped off. So that stuff in the late 90s, early 2000s, from a statistical standpoint, is an outlier. It has to be attributed to something. Right? Somebody hitting 72 home runs in a season when the average is half of that, something's probably going on. Right? And there's a whole field of statistics that's just attributed to baseball called sabermetrics, where they look at that type of stuff. All right? People make a lot of money doing it. All right. The other two imaginary fences, the outer fences, are defined at a distance 3 IQR. So that's a long ways from the middle. And notice they're not written on there. They're just imaginary, right? The other ones were 1.5, right, to find the lower and upper inner fence. The other two are defined at 3 IQR, so a lot farther below and above. Are very extreme measurements that require special analysis. Since less than 1/100th of 1%, or 0.0001 of the measurements for mound-shaped distributions are expected to fall beyond the outer fences, these measurements are considered to be outliers. We're not really going to mess with that too much as far as our box and whisker. We're going to use another analysis to determine this. all right, our numerical analysis. Because there are no measurements of gas mileages beyond the outer fences, there are no outliers. So the stars are just potential outliers. They could be, but we're not sure. That's like somebody hitting 56 home runs when the average is 35. Right? It could be, but we're not sure. Recall that outliers may be incorrect recordings, members of a different population, which wouldn't make a lot of sense. That'd be like finding the gas mileage of a motorcycle when all the other ones are cars, right? That's a whole different population. Because motorcycles get a lot better gas mileage, right? Like they only have a 4 or 5 gallon tank, so they better get pretty good gas mileage, right? You're going to be stopping and filling it up a lot. Or at least a very unusual measurement from the same population, which does happen. You notice how they write that as the last one? The other two happen more frequently than this very last one. This rare occurrences doesn't happen very often. The box plot of figure 2.31 detected 2 potential outliers. That's because they lie outside of the inner fence, not the outer fence. All right? The outer fences are 3 IQR. Okay? The 2 gas mileage measurements beyond the inner fences. When we analyze these measurements, we find they are correctly recorded. So it wasn't because of reason 1. Perhaps they represent mileages that correspond to exceptional models of the car being tested or to unusual gas mixtures, which could be the problem. Maybe they were at a different elevation. Elevation affects gas mileage. All right? That could have been it. All right? Outlier analysis often reveals useful information of this kind and therefore plays an important role in the statistical inference-making process. This outlier analysis stuff, I mean, people contribute their whole careers to doing that type of thing, right? Which you kind of look at it and you're like, man, how could that be? But when you have humongous data sets with lots of variables, it takes a lot of time to detect these outliers. And to know if it's an outlier because of an issue with recording the data or an issue with pulling it from the wrong population, or is it actually something that's rare? Right? What's our inference on that? What are we inferring? Is this rare event going to happen again? Right? That's something else you would ask. In addition to detecting outliers, box plots provide useful information on the variation in a data set. Variation in a data set is spread. The elements and nomenclature, that means basically the words that are used when describing it, all right, the English behind it, of box plots are summarized in the box. Some aids to the interpretation of box plots are also given. So here we go, elements of a box plot. This book's nice because it gives us these nice blue boxes that kind of give us a synopsis of what we've talked about. All right? So first, the box. We create the box. The hinges of the box are at QU and QL. The 25th and 75th percentile. So let's kind of draw this out. Here's my red marker. So I'm going to draw just an arbitrary box and whisker, and I'm going to do it left to right, where that other one is vertical, which is just an orientation, all right? So, the box, so here's our graph, all right? So here's our box right here. It's always divided in half. This is always the median, which is the 50th percentile. On the low end is got to be QL. And what percentile is it? 25th. And then QU, which is the 75th. That's our box. Right, and down here is the observations. The width of the box, the vertical axis here really doesn't have much meaning, okay? In this case. Just like when we looked at the box from this page, notice how there's nothing written on the horizontal axis. It's just on the vertical axis. So what I'm basically doing is taking this and flipping it on its side, right? Which is just an orientation. Doesn't really matter how you draw it. So the box with ends at the hinges. So these are the hinges. right? Hinge and a hinge. Or if you're a good artist, maybe you could draw a hinge on there. You know, to kind of help you remember that it's a hinge. So there's our box, the median's in the middle, there's our hinges. All right. Now it could be, this median could be pulled a little closer to QL or to QU depending on where all the observations lie. Right? If there's a bunch more that happen right here, then the median's going to be pulled that direction. The median is not always in the center of the box. Okay? The points at distances 1.5 IQR from each hinge mark the inner fences of the data set. Lines, the whiskers, are drawn from each hinge to the most extreme measurement. All right, so this is the hinge, or this is the whisker, and the whisker. So the inner fence, when we construct the inner fence, we basically go and then look for the outermost measurement and then create a whisker. So the inner fences and the whiskers are basically the same. The inner fence could extend longer than the whisker because the inner fence might go past the most extreme measurement inside the fence. But this is QL minus 1.5 IQR. And this is QU plus 1.5 times IQR. And those are our whiskers. What is IQR? Well, this entire distance right here is the IQR. Right? It's the distance from the upper to the lower quartile. And then finally down here I'm going to put a dashed line to represent the outer fence. Okay. So this is QL minus 3 IQR. That's our outer fence. And this is our other outer fence, QU plus 3 IQR. So the whiskers only pertain to the inner fences. Okay. So this graph is basically a general drawing of what's going on inside this box right here. Okay? And these formulas will be given to you, but you have to know what QL and QU. How do you find QL and QU? Once you find QL and QU, all this other stuff bleeds directly from it. Right? Right. And then we use an asterisk to represent actual data values that fall outside the whisker but inside the dashed line. Anything that falls outside the dashed line we're just going to call an outlier. Right? We use asterisks to represent potential outliers. Right? So asterisks are potential outliers. I'll put that down here. Potential outliers. Why did I put a Q? I've been drawing so many Qs today. So that's very important. If it's outside the outer fence, it's not a potential outlier. It is an outlier. Okay? And then they use a 0 is used to represent measurements that lie beyond the outer fences. So that's way outside. Thus, outer fences are not shown unless one or more measurements lie beyond them. That's why I just draw the outer fences with dashed lines right here. Okay? Now, where this 1.5 and this 3 comes from, it has a little bit to do with standard deviations, but just take it with a grain of salt. That's the way it's constructed. All right, that's the formula. The symbols used to represent the median and the extreme data points will vary with the software used to construct the dot plot, or the box plot. Most of the time, median is a capital M, right? Just like I've written here. Capital M is the median. The median is always the 50th percentile. Right? Isn't that what a median is in the road? 50% of the road lies on one side of the median, 50% of the road lies on the other side of the median. And then, if you use a different software to construct these, it might use different symbols to represent these things, so you need to consult the program's documentation to determine exactly which symbols are used. They're going to change depending. You might be in a science class one day that uses a whole different type of software, right? You might be using pivot tables in Excel, and it uses a little bit different information. And as you read through this, you probably think about stuff that pertains to your major where you need to know these type of things, right? People that are SLP, speech language pathologists, right? If you're testing enunciation of words, you want to know if there's a certain student that has a really bad, say, stuttering problem, right? And then you can actually put statistical evidence to show that they have a bad stuttering problem. Because you give 50 kids the same thing to read. Most kids are at about 6, 7, or 8 stutters, and one kid's at 25 stutters. That looks like it's an outlier, but you're not sure. You can actually plug it into this type of stuff and statistically show that it's an outlier through empirical evidence, stuff that can't be, taken down. It's not opinion; it's fact. All right. And then here's some stuff, just some aids in interpretation. The line median inside the box plot. So the line inside the box is always the center. And notice center is in quotes right there. That's because it's not always going to be directly in the center. This median could be pulled closer to QL or to QU depending on where all the data is. I mean, there might be a lot of miles per gallons that were right at 36 miles per gallon. Right? So this median would be pulled this direction, but QL wouldn't move. That's why center is in quotes right there. Right? Examine the length of the box. The IQR is a measure of the sample's variability, and is especially useful for a comparison of two samples. Right? Visually compare the lengths of the whiskers. If one is clearly longer than the other, the distribution of the data is probably skewed in the direction of the longer whisker. So if I was going to do a box plot for this one, for skewed right, here, let me just kind of erase it and kind of show what it would look like. This is one where QL, so there's QL, there's QU. Here the median would be pulled towards QL. And now let me put a capital in. And then I would have a longer whisker over here and a shorter whisker to that side. And the median would be kind of pulled towards QL because that's where the meat of the curve was. Kind of see what's going on here? See how that's skewed to the right? That's what this is talking about. Visually compare the lengths of the whiskers. If one is clearly longer than the other, the data is probably skewed to that direction. And conversely with this one, let me erase this. Right? Notice the median would be here, but most of the data will lie to the right of the median. So the median is going to be pulled towards QU. Like this. So we have there's our box, there's QU, there's QL. Here the median would be pulled towards QU. We'll have a shorter whisker on the right and a longer whisker on the left. See how the median isn't exactly in the center of our interquartile range? So that becomes a lot easier to see where the skew is when it's whiskers. Whichever one has the longer whisker is the direction it's skewed towards. Analyze any measurements that lie beyond the fences. Whether it's the inner fence, which is 1.5 IQR, or the outer fence, which is 3 IQR. Less than 5% should fall beyond the inner fences, even for very skewed distributions. Measurements beyond the outer fences are probably outliers with one of the following explanations. A and B, which means we would kick it out because it was bad data recording or bad population, or it's actually an outlier. It's actually a rare event. The measurement is correct and from the same population as the rest of the sample. Generally, we accept this explanation only after carefully ruling out all the others. So like tornadoes, right, on a certain day. You know, we're kind of in tornado season now. You go in the Midwest. Most tornadoes are about a 1.5 to 2 on the F scale. Very few are actually F5s, which are a mile in diameter, right, at the base of them. So those are outliers. They don't happen very often. All right, we'll get 1,000. For every 1,000 tornadoes that touch down, there might be 1 or 2 F5s. And they cause the most damage, right? Hopefully, they happen somewhere that's not very populated, right? Unlike the one, what was it, about 3 years ago that went through Tuscaloosa, Alabama, and did a lot of damage. It was an F5 tornado. And then scientists like to know how likely F5s are so that they can say, well, this one has the potential to be an F5. They can warn people, right, and save lives. Right? So that's what they're after. That's why, has anybody ever seen the old movie Twister? Yeah. Where they send all those little data balls up into the tornado? That's what they're doing. They are collecting data so that they can make inferences about the future. So they can say, well, based on the characteristics of this tornado, we expect this, this, and this to happen. So that then they can make a prediction in the future. All right? If the barometer is at a certain level, maybe it has more potential to switch direction or whatever it might be. Okay? Refer to the psychological science experiment called the water level task. Oh, and that's something we hadn't really looked at, but we'll look at the graph. And then here's a box plot of it. So here's an example where the median is not directly in the middle. You'll notice this data set has potential outliers that lie above it, but nothing that lies below it. Right? But this one's kind of opposite. You'll notice here the median is pulled to the opposite side of the outliers in those cases. So this one's a little bit different. But it's still the same thing. It's got our lower hinge, upper hinge, our QL and QU. The line is our median. And then this is QL minus 1.5 times IQR. And this line is QU plus 1.5 times IQR. Where the IQR is basically this distance right here, right? From QU to QL. So it's no coincidence that this line looks roughly about 1.5 times the width of that box. That's how it's set up to be. Okay?
Does it matter which way you're going?
No, it doesn't matter. I like horizontal orientation myself. It doesn't matter though. What is important is that you label. These labels are what's really important, right? That I know what the data is. But it doesn't matter. Yeah. That's why I like to show you in both ways. Okay? Yes, this will be on tonight's. And there is well, there's not a video for creating these box plots, but there is one for the scatter plots that we'll talk about in the next section. These you'll just have to read and interpret. All right? I'll give you a box plot. I'll say, where is QL from the box plot? And it'll be easy to identify. All right? It won't be like, this one you kind of have to estimate, right? QU is roughly, what, about 2.5? The stuff for your homework, it'll be easy to identify where the values are. And then it might ask you, how many potential outliers are there? And what would be your answer? 2. How many asterisks are there? Do they lie above QU or below QL? They lie above QU. All right? That's the type of stuff you'll have to answer. Those type of questions. Okay. So here's another example of a PhD student in psychology conducted a stimulus reaction experiment as a part of her dissertation research. You have to do a dissertation before you get your PhD. Similar to a thesis, but a lot more involved. Thesis is for your master's. She subjected 50 subjects to a threatening stimulus and 50 to a non-threatening stimulus. So, the threatening stimulus could have been a bee in the classroom. All right, something you feel threatened. Or a non-threatening stimulus like maybe music. Right? Classical music could have been a non-threatening stimulus. The reaction times of all 100 students recorded to the nearest tenth of a second are listed in Table 2.9. Look at this. What do you notice about the times for the threatening stimulus? They're all a lot smaller, right? There's not even hardly any 2s. Where up here, there's all 2s. This basically is empirical evidence to show that we have a fight or flight reaction. Right? When we get a threatening stimulus, our senses all increase. Our sight, smell, sound, everything goes up when we're threatened. This shows that people have that. Your adrenaline goes up, all that stuff, right? Everything peaks. As opposed to non-threatening, where it's just music and you don't really get any reaction. It's pretty interesting when you look at this. So let's look at it in a graph form, which is on the next page. So there's the box plot for it. And then in this one, in SAS, the median is represented by the horizontal line, while the asterisk is the mean. Here the asterisk isn't a potential outlier, right? It depends on the software system. Right? Analysis of the box plots on the same numerical scale reveals that the distribution of times corresponding to the threatening stimulus lies below that of the non-threatening. I mean, if you look at it, the upper whisker, the upper fence for the threatening is nearly at the median for the non-threatening. That is very strong evidence to show that the reaction times when you get a threatening stimulus are much quicker. There it is, right there, black and white. This one is skewed up, right, or to the right, which is why I like to do it in a horizontal orientation so that you can say left or right when we're talking about skewness. So you'll notice this one's skewed towards longer times. This one's skewed towards shorter times. See how the mean is below the median? Which is what happens when it's skewed to the left. So there's a tendency to be shorter on time. I mean, look where this lower quartile is. It lies below the lower fence for this other one. So that is definite evidence to show that when you get threatened, you react quicker. And that's natural. I mean, that's nature right there in black and white. Okay. The researcher concluded that the reactions to the threatening stimulus were faster than those to the non-threatening. However, she was asked by her PhD committee whether the results were statistically significant. Does it really matter? Their question addresses the issue of whether the observed difference between the samples might be attributable to chance or sampling variation, so just pure chance, or rather than to real differences between the population. To answer this question, the researcher must use inferential statistics rather than graphical descriptions. We will discuss how to compare two samples by means of inferential statistics in Chapter 9. That's what we're leading up to, all right? We're actually going to try and answer this question. Is it statistically significant? I try to put those two words together. Statistically percent. All right? So this is the stuff we're going to get to in Chapter 9. We'll look at that data and we'll actually say, yes, it is significant, or we'll say, we're not sure. We'll either reject or fail to reject. Okay, so that's graphical interpretation of outliers. And I know I'm kind of running over on this section, but the next one's not very long. So the next one is pretty simple, though. Z-scores really make our life easy, and you'll see why. Z-scores can be used to detect outliers and make inferences. Okay. Problem. Suppose a female bank employee believes that her salary is low as a result of sexual discrimination. Basically, she's saying, are males that do the same job as her getting paid more? Right? That's what she's asking. And we've kind of seen through a big scale that this is true in some cases, right? To substantiate her belief, she collects information on the salaries of her male counterparts in the banking business. So males that do the same job, right? She can't pick males that are tellers, right? That's a different population. It's got to be people that have the same title. She finds that their salaries have a mean of $64,000 and a standard deviation of $2,000. Her salary is $57,000. So is her salary lower because of sexual discrimination, or is it because a lot of the people that are in here for this $64,000 have more time in and other things, right? They've spent more time with the company, they've got more bonuses, whatever it might be. Just by looking at this, you would say that definitely she's on the lower end of the scale, right? But is that because of time in the job or other factors? So here's a graph of it. So first thing she does is writes her Z-score. This is something that is due tonight, right? As Z-scores. It's the observation, her salary, minus the mean salary divided by the standard deviation. That formula for Z we will see over and over and over again, right? So you have to be able to plug the values in. You'll notice if her salary was $64,000, her Z-score would be 0, right? Because we'd be subtracting the same two things in the numerator. Her Z-score is negative 3.5. What's the unit on Z? What's the unit of the Z-score? Always. It's standard deviations. So that means her salary is 3.5 standard deviations below the mean. That's pretty low. I mean, anything outside of 3 standard deviations above or below is not going to happen very often, right? As for the graph that I erased on this board, where remember way out at the tails it was 0.15% and 0.15%. So 0.3% lie outside of 3. The implication is that the woman's salary is 3.5 standard deviations below the mean of the male salary distribution. Furthermore, if a check of the male salary data shows that the frequency distribution is mound-shaped, which we haven't done yet, right? We can infer that very few salaries in this distribution should have a Z-score less than -3, as shown in 2.34. How would they check to see if the data is mound-shaped? What two things have to be equal? The mean and the median, right? So they need to look at all the data and see if the mean and the median are approximately the same. Right? But if you're not sure it's mound-shaped, you can still use Chebyshev's, right? So 3 standard deviations is 88.9%. We know that's going to happen no matter what, regardless of the shape. So if you fall outside of that, you're still in only, what, the 11%, which is still a pretty small amount, but not as small as if we know it's mound-shaped. Clearly, a Z-score of -3.5 represents an outlier. Either her salary is from a distribution different from the male salary distribution, or it is a very unusual measurement from a salary distribution no different from the male distribution. All right? So it's either from the wrong population or it's a rare event. Which of the two situations do you think prevails? Statistical thing would lead us to conclude that her salary does not come from the male salary distribution, lending support to the female bank employee's claim of sex discrimination. However, the careful investigator should require more information before making this inference. We would want to know more about the data collection technique the woman used. Right? We want to make sure that she's not just getting males that have been at the job for 25 years or more, and she's only been at the job for 4. Right? That wouldn't be fair. So you got to make sure where she's getting the data collection from. And more about her competence at her job. Also, perhaps other factors such as length of employment should be considered in the analysis. All right? She should only be comparing herself to male salaries with the same amount of time in. Because that's how raises happen, right? Is after time in. That's basically how they happen. So you want to make sure what you're comparing to is basically the same population. You don't, right? You want to be representative. Okay. Okay. Examples 2.7 and 2.1a exemplify an approach to statistical inference that might be called the rare event approach. An experimenter hypothesizes a specific frequency distribution to describe its population. So right there, they hypothesize the distribution. So they say, this is what we think it will be. So right there, you're already introducing some error, right, when you're hypothesizing. Then a sample of the measurements is drawn from the population. If the experimenter finds it is unlikely that the sample came from the hypothesized distribution, the hypothesis is judged to be false. Thus, in example 2.18, the woman believes that her salary reflects discrimination. She hypothesizes that her salary should just be another measurement in the distribution of her male counterparts if no discrimination exists. However, it is so unlikely that the sample, in this case her salary, came from the male frequency distribution that she rejects that hypothesis, concluding that the distribution from which her salary was drawn is different from the distribution for the men. That stuff we'll get into. All right? I know that's kind of circular, right? You're probably thinking to yourself, well, what distribution would it be from if it's not from the male one? And that stuff we'll talk about. All right? Basically, what was the population that created the distribution? Is it similar to what her sample would be? Right? Does it have the same characteristics? Right? You wouldn't want to compare yourself if you're at a bank in rural Iowa to somebody at a bank in Manhattan, right? Because of course their salaries are going to be a little bit higher. So that's what that's talking about. All right. We conclude this section with some rules of thumb for detecting outliers. Box plots. Observations falling between the inner and outer fences. So, between the whisker and the dotted line. So if it's outside the whisker but inside the dotted line, we call them potential outliers. Observation falling outside of the dotted line are deemed highly suspect outliers, which means they're outliers until we go in and look. Those are kind of guilty until proven innocent, is a way to think about those. All right? Whereas the potential outliers are innocent until proven guilty. The Z-score and box plot methods both establish rule of thumb limits outside of which a measurement is deemed to be an outlier. Usually the two methods produce similar results. However, the presence of one or more outliers in a data set can inflate the computed value of X. Right? If our data set is more variable, it could inflate the computed value of our standard deviation. Consequently, it will be less likely that an errant observation would have a z-score larger than... Notice this is absolute value of 3, so that means less than -3 or +3. That means 3 standard deviations below the mean or 3 above. Whereas, in contrast, the values of the quartiles used to calculate the intervals for a box plot are not affected by the presence of outliers. So sometimes you'd like to use a box plot, sometimes z-scores are better. It's basically what that's saying. Because the median, remember, isn't influenced by outliers like the mean is. All right. So this is basically what we want to get out of this section. All right? So there's suspect outliers, innocent until proven guilty, if they lie between the whisker and the dotted line. If they lie between 1.5 and 3. That's positive 1.5 or 3, or negative 1.5 and negative 3. If they're outside of the dotted line, they are guilty until proven innocent. They are highly suspect outliers. Remember, all these values come from QL and QU. IQR is the difference between QL and QU. And then z-scores. Observations with z-scores greater than 3 in absolute value. So that means the z, we take away the negative. If it's negative 3.5, the absolute value of negative 3.5 is 3.5, right? You basically just drop the negative. So they use the absolute value so they don't have to say z less than negative 3 or z greater than 3. That's why they use absolute value. So greater than 2, if it's more than 2 standard deviations away from the mean, it's a possible outlier. If we know it's more than 3 standard deviations away from the mean, it is an outlier. All right, remember Z, the unit on Z is the number of standard deviations. Okay, so this little piece right here basically talks about everything we've done today. So far. Okay? And then here's another thing talking about this body image data, which you notice this has happened at the end of every section. It does this thing about body image. So that'd probably be a good way to study for the test. Go back through this body image, start with section 2.1, read through it because it kind of builds on itself each time. All right? So they ask them about this body image, and they ask them to rate it on a scale, right, ranging from 7 to 35. Are you not satisfied with your body image, or are you very satisfied with your body image? Right? Which is definitely an opinion. But this is one of those where they take a qualitative thing and make it quantitative by putting it on a scale. Right? Okay. Last section. This one's not very long. It's just finding these. Is there a relationship between two sets of data? That's all we're talking about. And this is like 2 pages. This is a very, very short section. There's a few definitions, and that's it. All right? Okay. So the claim is often made that the crime rate and the unemployment rate are one and the same. High unemployment means high crime. Low unemployment means low crime. Have you guys heard that before? Is that true? Right? You could correlate, is a town that has a lot more college students in it going to have more alcohol sales, right? Is that correlated? Is a town that has a lot of older people living in it, maybe a retirement community, are they going to have more doctor's offices, right? Things like that. Are they correlated? So, another popular belief is that smoking and lung cancer are related. I don't think that's a belief anymore, right? We've shown that it's related. Some people even believe that the Dow Jones and the links of fashionable skirts are associated. Now listen to that. What they're saying is fashion trends go with the stock market? Is it? I'm not really sure. I know that the stock market kind of goes in waves. You know, it's up for a couple years, it's down for a couple years. Fashion's kind of that same way, right? Stuff's hot for a little while and then it's not, right? It goes up and then back down. And it's kind of cyclical. Stuff kind of comes back. Now that's kind of an interesting assumption right there. I don't know if that's true or not, but let's read through. The words correlated, related, and associated apply a relationship between two variables. In the examples just mentioned, two quantitative variables. Right? So in all 3 cases, we can come up with a quantitative. The number of people who smoke, the number of people who get lung cancer. Right? One way to describe the relationship between 2 quantitative variables called a bivariate relationship. So a bivariate relationship is a relationship between 2 quantitative variables. Does taking more math classes mean you have a higher paying job when you finish school? Or STEM, right? Taking more STEM classes, does that mean you have a higher paying job? Right? Does going to graduate school mean you have a higher chance of employment? All that type of stuff. All right? The way we do that is by constructing a scatter plot. A scatter plot is a 2-dimensional plot with one variable's values plotted along the vertical axis and the other along the horizontal axis. So one we would have unemployment and the other we would have crime rate. One that I do for my algebra classes, especially college algebra because we cover so much stuff and attendance is so important. And I basically show them this graph almost after every test. It's a graph that does this. So this graph down here would have been test score, Ooh, C-O-R-E. You spell that right. Test score, so we go from 50 up to 100. And over here I would put days missed. And it would go from 0 up to 10. What I've noticed is the more days you miss, so what I would do is I'd take a student's test score, find the number of days they missed, and plot a point. And you know what this graph would start to do? It would look like this. Just about every time, that's what the graph would look like. Now, there would be a dot here sometimes and a dot there sometimes. But for the most part, as your number of days missed decreased, your test score went up. There was a definite relationship between that. All right? This class, there's not quite enough people to establish that. You know, you need about 25 or 30 observations to really create a good scatter plot. But that's something that was definitely associated. All right? That makes sense what I'm talking about over there? When we're associating two things? Right? For example, figure 2.35 is a scatter plot relating the cost of a mechanical work to the floor area of the building. What do we think is going to happen there? You know, and think about like when you buy in bulk. When you buy stuff in bulk, what happens to the price? It usually goes down, right? So when we're talking about work, as you do more and more work, you would expect the total cost to go down a little bit, right? Slightly, not much, because a lot of this stuff is done by the hour anyway, so it's all the same, right? Whether it's 10 square feet or 1,000 square feet, you get charged the same amount per square foot. But then when you have a bigger job, you don't have to worry about moving stuff in and out. All the equipment's already there, so they can get to work a lot easier as they get into the job. Right? Note that the scatter plot suggests a general tendency for mechanical cost, oh, see how I said it backwards, cost to increase as building floor area increases. Yeah, if there's more stuff to work on, then the building floor area increases. And then here's that graph. But if you get all the way out here, notice there's a couple that are really big where the price tends to fall back down. So it almost looks like it's a parabolic type motion. Right? You guys see that? So cost of mechanical work and then floor area in 1,000 square meters. Looks like whoever this was kind of got took a little bit, right? They paid a little bit too much. Because there's some people over here, there's 1, 2, 3, 4, 5 observations that have more area that didn't cost as much. Right? So you kind of see it start to trend back down after you get past, what, about 3,500 square meters of floor space. All right? When an increase in one variable is generally associated with an increase in the second variable, we say that they're positively related. Which is just like the slope of a line. If you look at the slope of a line and it increases as you go from left to right, it has a positive slope. So this one wouldn't be positively related, it would be negatively related because it decreases. As one gets bigger, the other one gets smaller. Right? As test score gets bigger, days missed gets smaller. So that would be a negative correlation. And then here's 3 examples. So something that could be this is height and weight. Right? Wouldn't you say height and weight are basically a positive relationship? As you get taller, you get heavier. That's just natural, right? This one is just like the one that I just showed. As your number of test days days missed decrease, your test score actually goes up. Notice how the smaller values are always towards the origin, right? It's not like I wrote this from 100 to 50, right? You always get bigger as you go from left to right and get bigger as you go from bottom to top. And then it's possible that there's no relationship. I mean, you could do this with a lot of things, right? You could do like deer in the summer when they're moving around. Right? They tend to move around a lot more in the morning and the afternoon. Right? So you see it in the peak hours of the very morning and then the hours of the afternoon. So there is a correlation between deer movement and the time of day. Right? And if you're a guy that does guiding, you want to know that, right? Or a girl, anybody that does that. That's the type of stuff you want to know. A formal definition of correlation, which is a very specific word in mathematics, the word correlation, is given in chapter 11. There we will learn that correlation measures the strength of a linear or straight line relationship between two quantitative variables. If you've ever constructed a graph in Excel, I know we did that a little bit in 106, and you put a linear line on it and it gives you a little r squared value. It says r squared equals 0.972. That's your correlation coefficient. That tells you how correlated the two things are. The closer to 1, the better. Now, obviously, this has no relationship right here, right? That could be day of the week and color of clothes. Right? That really doesn't have. Maybe Fridays you might wear green here at Eastern, right? Because of sports or something, but that would be about it. So that's all this is saying. Positive, negative, no. So let's go look at this next example and look at its correlation, or its association. A medical item used to administer to a hospital patient is called a factor. For example, a factor can be an IV fluid, needles, shave kits, bedpans, diapers, dressings, medications, and even code cards. The coronary care unit at Bayonet Point Hospital in St. Petersburg, Florida, recently investigated the relationship between the number of factors administered and the patient's length of stay. Now, wouldn't you think the more factors, the longer the stay? Right? Doesn't that kind of seem like it would correlate? Data on these two variables for a sample of 50 coronary care patients are given in this table. Use a scatter plot to describe the relationship between the two variables of interest: number of factors, number of IVs, bedpans, medications, dressings, diapers, and length of stay. You'd expect them to be positively correlated, I would think. And here's the graph. The graph would support that that's positively correlated. The reason is because notice down here it's pretty empty, and up here it's pretty empty, right? For a long stay, it's not like there's people that only have 10 factors, right? This person right here had a kind of a long stay, 6 days, and didn't use very many factors at all. But as your number of days increase in the hospital, the number of things you use increase as well. So a hospital likes to know this data so they know how much stuff to have on hand, right? What type of stuff and how much do we need? Right, if we have 10 patients, do we need 1,000 bedpans or do we need 100? That type of stuff, all right? How often do we need to order them? Right? That's stuff hospital administrators really want to know, right? This type of data. But you can see as the horizontal increases, the vertical increases. So I would say it's not a strong relationship, but it definitely is there. So it says, rather than construct the plot by hand, we resort to a statistical software package, the SPSS plot of the data in Table 1.0, Table 2.10, with lengths of stay on the vertical and factors on the horizontal. Although the plotted points exhibit a fair amount of variation, the scatter plot clearly shows an increasing trend. It appears that a patient's length of stay is positively correlated with the number of factors administered, which is what we would expect. If hospital administrators can be confident that the sample trend shown in Figure 2.37 accurately describes the trend, then they may use this information to improve their forecasts of lengths of stay for future patients. All right. The scatter plot is a simple but powerful tool for describing a bivariate relationship. However, keep in mind that it's only a graph. No measure of reliability can be attached to inferences made about bivariate populations based on scatter plots. We'll actually talk about statistical tools that allow us to make inferences about bivariate relationships all the way in Chapter 11. That'll be one of the very last sections that we cover. right? And it's an optional one. Hopefully we get to it because it's really neat, right? It does a lot of cool stuff. The stuff in this class is very useful, right? I mean, it's basically becoming a good consumer of information. That's what statistics is, right? Are you a good consumer of information? And especially numerical information. Okay? So here we go. Slug percentage. Let's just look at this example, just because we've got a little time. Does elevation impact hitting performance in baseball? Yes or no? The Colorado Rockies play their Major League home games in Coors Field in Denver. Everybody knows Denver's a mile high. Most people don't know Santa Fe is higher than Denver. But it is, right? Each year, the Rockies are among the leaders in team batting statistics. Whether that's home runs, batting average, slugging percentage basically deals with how many bases you get per hit. So when you get a hit, do you get 2 bases? Or do you get 1 base? Or do you get 4 bases? All right, that's what slugging percentage deals with. Many baseball experts attribute this phenomenon to the thin air of Denver. And it actually is true. Things go farther at a higher elevation. I mean, that's been statistically proven. A projectile launched at sea level at the same angle and velocity goes shorter than something launched at elevation at the same angle and velocity. All right, that's statistically proven. Investigated the effects of elevation on slugging percentage. Basically, they're looking to see if balls go out of the yard, if there's more home runs based on elevation. It's kind of what they're looking for here. All right? So what they do is they go to each city's elevation and then get the average slugging percentage. Anaheim is at sea level, right? I mean, basically, it's 160 feet, but that's in L.A. Arlington's in Texas. Atlanta, Baltimore, Boston. There's not really any high cities except for Denver, right? Denver's really the only one. There's not a team in Salt Lake in baseball, right? St. Louis, man, I thought St. Louis was a little bit higher than that. That's pretty surprising. I've never been there before, but that's a pretty low elevation, really.
Well, it floods from the river.
Right, yeah, from the river, but not from salt water. But that's pretty low, really. Lower than I thought it would be. Look at Tampa. It's 10 feet above sea level. There's not a team in New Orleans because it would be negative on here, probably, right? They're below sea level. So what they do is construct a scatter plot, which we're not going to do because we don't basically have all the data. But I mean, just looking at this, you can see that. See how this is a 10 elevation? Look, it's a 500. You can kind of see that as the elevation goes up, it looks like the slugging percentage goes up. Not really in Atlanta, though. Atlanta's kind of low. But look how high Denver's is, 0.625. That's by far the highest of those. So just by looking at this data, we would say that there's a positive correlation between elevation and slugging percentage. All right? Okay, so these two sections are due tomorrow by midnight. So make sure you always click this show all button so that your quizzes show up. Which what your quiz is has questions from the entire chapter without help. All right, it doesn't have to show an example or the textbook. All right, it's basically like a practice test. So these two, 2.8 and 2.9, are due tomorrow by midnight. I have right here your study guide for the exam, all right? Which doesn't have example problems on it. It just has stuff that you need to know, all right? The example problems are contained right there in that quiz, okay? And you can also go find problems in your book. The formulas that have NC on them mean that you're going to have that formula on the test, all right? That'll be on your formula sheet. So make sure you know how to use it. You understand what it means. Okay? I just noticed here, there's one small typo I just noticed right here. Let me mention it to you. Look at part B for the variance. And this isn't necessarily a typo, but this sum should just be in the numerator, right? It's just sum of x over n. There's no sum of it, sum of n. So this sum should only be written in the numerator right there. Right? There you go, like that. But that's not really a typo, but there is a typo right here in part B. Does anybody know what it is? It's in this formula. What's in this formula that's not in that formula? The n minus 1, right? This needs to be divided by n minus 1 as well. But we don't really use this formula. We use this formula when we're doing it by hand, right? It's a lot easier to use this formula. This is the one on your homework that was due last night. You had to use this formula a lot, right, to create your standard deviation, or your variance, which is what s squared is, and your standard deviation, which is what s is. All right? Range, empirical rule, Chebyshev. And then 11 and down talks about box plots, so make sure you know how to interpret a box plot. Right? So this study guide basically has everything you need to know. Know your definitions. Look how many that are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 definitions right there in question 1. Okay? I could ask you a fill in the blank. I'll give you a definition and say, what is it? Right? Be ready for that. Okay, so tomorrow we're going to study for the exam. We'll meet in here and then go to the computer lab, I think. All right? All right, thank you, everyone. Where's my sign-in sheet? Everybody sign in. Sign. All right, thank you, everyone. We've covered everything that's going to be on the exam. Okay? And I'll send out the media site link here in a little bit for today's lecture. Okay. Thank you.
I have a question.
Yeah.
So I have a
Okay.
board, and I have a stat button, but I don't know where to put the data. Or just
Right here, okay. So when you get your stat button, see how it's got all these different tests, calc, so you want to do one variable stats, you hit enter right there. Oh, it's already got it in.
Okay.
So that's how you pull up all of your stuff.
Okay.
But we got to find some. It's a neat calculator.
Yeah, I really like it.
Watch, here's how you find that out. Go to Stat, Edit. So you go to Clear, so go Stat, Edit,
Oh, okay. So,
List. So then you can enter in 5, you know, so
okay.
then go Stat, Edit. Yeah, you can do multiple lists, which is nice.
Okay.
So let's go there. So then you can go back to Stat and actually calculate. Look. There it is. And there's 6 measurements. There's your mean, S of X, there's your standard deviation.
Okay.
All righty?
Awesome.
Cool.
Thank you.
No problem. Google's awesome.
Yep.
I didn't do
The one from last night?
yeah. 'Cause
Which you can still do.
Yeah,
course.
I didn't want to just kind of guess and get like right answers and not know how to do it. 'Cause
Right.
I don't know what I missed. I took notes that day, but
From the lecture? Or
Yeah.
you watched it online?
no, not yesterday's, or Thursday, sorry.
Oh, okay.
Yeah, the one that was due last week.
Okay.
The,
Well, you want to go to my office and
Yeah,
look at
that's
it?
fine.
Okay, yeah, let's go do that. Let me erase this stuff in here.
I did good at first, and then like when I got to 5, I started.
Yeah, it's probably, you're just misinterpreting what it's telling you. Probably nothing too drastic.
But the stuff today, I think I understand.
Isn't
it.
too bad?
No,
Okay.
yeah, like, I totally understand.
Well, once you can find your 75th and 25th percentile, which you just basically count them, right, and get to 25%.
Is that what we did yesterday?
No, that's what we did today.
Okay.
Well, yesterday we talked about it, but I never really did any examples of it. But it's basically, you put it in ascending order, and say you have 10 themes. The lower 5 is your 50 percentile, right? Your upper 5. So it's really not very hard to find the percentiles. And with a little practice, I think you'll be fine with that.
Yeah, the reviewer told me with no examples to show.
I know, right? Well, yeah, it's kind of a practice test. Where, a good thing to remember is reviews are usually more challenging than the test for any class, right?